I just need like maybe less than half an hour and then we'll be done. Okay. So let's have a look at the rest of the material. Now, I just want to do a little bit of summary of this, what we have spoken before. So for the heat pipe, it's actually a very efficient way of doing heat transfer. So we have spoken before that this phase change requires, and phase change doesn't mean from liquid to gaseous. For the heat pipe, it's also from the gaseous part back to the liquid part. It requires a large amount of energy. And the good thing is that it can be the liquid or the gaseous form, it can be easily transported. Now what does that mean? You could see that for this heat pipe over here, it's easy to transport it across, sort of like a longer distance, and yet it's still effective on these two ends. So it can be easily transported, whether it is in the gaseous state or the liquid state. So maybe not leave your gas and liquid. The gas and liquid can be transported very easily. So this kind of system is very desirable. Transported easily around a system. So the material phase change can be transported from one location to another location. So you could see that this from this location to another location. And material here is your working fluid. The best part of this is that it could reuse the fluid and hence allows efficient material use. So because the entire structure is enclosed, this entire structure over here is enclosed, so it actually allows the fluid to be efficiently recycled again and again. So this is very attractive to us. Now for the heat pipe, if I were to sketch the thermal circuit diagram, the thermal circuit diagram for the heat pipe, we can start from this, what I call the cap region. These two ends will have a cap, one cap over here and another cap. This cap will cap the two ends of the pipe. So if I were to sketch the thermal circuit diagram, you will start with that one. You will have a certain resistance for your end cap, or cap end. And this resistance is going to mostly come from that casing, the copper casing over here, as heat gets transferred into it. I want to figure out what's the entire journey from one side to the other side for this sort of heat transfer. So there's one side that will be the resistance, thermal resistance of the cap end. And is followed by another thermal resistance, R, that is for the fluid. So the fluid over here will be the fluid that's entering into this cavity over here. And as it enters into it, you're going to have two thermal resistances in parallel. What are the two? This one here will be a thermal resistance for the tube side walls. And what that means is that you could see for your heat pipe over here, this side wall could also have heat that is accepting toward the side. If you notice the figure that I showed you just now, very quickly, this figure over here, there's no thermal insulator around this surface. It's actually not necessary, and I'll tell you why later. So there's a thermal resistance where heat can actually transfer out. There's also another thermal resistance in parallel. That will be the resistance of the vapor transport. Now, what is this resistance for vapor transport? That comes about because you have this fluid that needs to be transported. You will get heated up over here, turning it into gaseous state, and it needs to be transported due to the difference in the pressure. And this difference in pressure would flow that gaseous state from one side to the other side. In this flow movement, there will be some resistance, and we call it the resistance of the vapor transport, although it's going to be very small. So after it reaches over here, you would have the same thing as what we had over here, R fluid, but actually this R fluid will be going out, not into the cavity. It's going out of the cavity. And finally, another part of the heat pipe, that will be the other cap end. Now, I want you to see which one of these resistance do you think will be the largest? Make a guess. Which one do you think will be the largest? The cap end. The cap end is actually made of, say, copper. So do you think the resistance that you're going to face over there is going to be large? Since copper has a pretty high thermal conductivity. It's going to be something that relates to the surface area. Which one will give you a large R? B. It's not going to be cap end, so you have 1, 2, 3, 4. A 25% chance of getting it right. Which one do you think will be your largest resistance? Please. Side wall, because side wall would have a large surface area. So this one will be large. So relatively, everything else is kind of like pretty small. Now, this R vapor transport is actually going to be even smaller. It is actually very small. But I want to highlight one thing about this thermal resistance. Especially the part where, if I were to ask you the question about this heat pipe, that if I have the entire heat pipe heated up instead of one end, the entire heat pipe that I heated up, meaning everything in there will be converted into vapor. If this is the case, then do you think you would have this term anymore? There wouldn't be that because there's nothing to get transported, given that everything else is in the vapor form. So this one, if no vapor, if there is no vapor phase, our vapor transport will be removed. That means there isn't that thermal resistance. What that means is that your R total now, without that part, your R total would be higher. And do you think you could see why your total resistance will be higher if you remove this? Yeah, if you remove this is in series now, and if this is large, then this is going to be dominant. Right, it's kind of electric circuit here. So the current that's flowing through here, do you think current would want to flow into something that has a high resistance or lesser resistance? Yeah, it kind of like wants to go through lesser resistance, so it could flow that way. But once you have the entire heat pipe that's turned into vapor, that means the inside working fluid has been turned into vapor, meaning you have actually overheated your heat pipe that's designed for that job. So the selection of heat pipe, hence, the selection of the working fluid in the heat pipe, hence, is very important. If you didn't select the correct working fluid, what's going to happen is that everything else got vaporized, didn't have a chance to condense at all. And if that happens, then your R tube side wall is as good as a copper rod now. So making your heat pipe not effective at all. Okay? So there's some figure over here. There's one figure over here. So actually, this figure I'm going to give it a star. This figure here I'm going to give it a star. And there's another figure over here. This figure here is actually a figure that we use a lot more in thermodynamics, but in this module or in this degree, thermodynamics is actually not delivered. If you were to sign up for SIE degree program, it's taught over there. But what you're seeing over here, just briefly, look at the condenser part. Now the condenser part is something that you see in the behind part of a fridge. So your fridge, that way, this is the behind part. Sometimes sealed up here, but you could see this kind of thing at the behind part of your fridge. What's happening over here is that this is called condenser. The condenser's job is to have, in the case of a fridge, natural convection. Natural convection. This natural convection is to cool down that compressed working fluid that's inside the pipe. If you compress something, actually that compression will increase the temperature of that fluid. Not sure is it intuitive enough, but maybe some of your, in some part of your life you have pumped the bicycle tire before. If not, maybe a ball, you pumped a ball before. Not sure, did you notice that after pumping, your pump actually feels a little bit hot or warm? That's because that pumping compression compresses all the molecules closer toward each other, very agitated, hence the temperature increased. So in the refrigerator, what happens is that there's a compressor to compress this working fluid. After compressing, it's passed back to the behind to let it cool down by natural convection. Why it needs to do that is part of the refrigeration cycle. I'm not going to talk more about refrigeration cycle, but there is that part that needs to be cooled down. So this figure over here is a pressure versus temperature graph. Over here, over in this quadrant over here, This one is your liquid phase. This one at the bottom part here is your vapor. And what happens in your condenser part, it changes from the liquid to the vapor state. So as you were to increase the pressure, what happens to the working fluid as you increase the pressure is that it will change from vapor state to liquid state. So you could imagine working fluid in vapor state. You could compress it under high pressure. As you compress it with a pressure that's high enough, you actually could see that it will be converted into liquid state at very high pressure. So the same works in the other way. If you were to decrease the pressure, taking water and put it into a container, and then if you evacuate the air, what's going to happen is that liquid water would vaporize because the pressure is very low now. So actually it doesn't require a lot of energy for that liquid state to jump into the gaseous state. So some of these things that was taught before in the thermodynamics. But what this slide is trying to say is that when we talk about the heat pipe over here, the speed of this fluid that runs from one side to the other side is your limiting factor. How fast could heat get conducted away? Right? So the speed of how fast this fluid can go from one side to the other side will be your limiting speed of heat getting transferred. Now I want to show you this video clip, and I'm not sure, could you hear, maybe it requires everyone to be kind of like quiet. Let's see if you could hear. How is it? Could you hear anything? Let's try using my speaker, right? can see from the video that the what heat pipe means to you now. It can really transfer heat almost instantly, depending on that pressure. It's how fast it could do it. And the amount of heat that it can transfer is the amount of latent heat of vaporization, the amount of heat. So we're trying to exploit that technology in a heat pipe to allow us to be able to do it. So since we've been talking a lot about the working fluid, now this slide over here kind of like lines out the various type of working fluid. Particularly, it labels a few types of working fluid. I'm just going to rewrite them, but rewrite them in terms of degrees Celsius, because maybe some of you find it hard to read, like 523 Kelvin. How many degrees Celsius is that? You need to have a sense of how hot that is. So I write a summary of this. You have the liquid helium. Now, obviously, to cool down liquid helium, you arrive at a very low temperature. So that one is minus 271 degrees Celsius to minus 269 degrees Celsius. That's for the working fluid in the heat pipe. Now, not all application will require such a low temperature, because remember, if you don't match that working fluid properly, you actually turn that heat pipe back into copper rod, because then you'll face a lot of thermal resistance, and you didn't make use of the resistance of the fluid transport. So if you look at other fluid that's out there, like mercury, it would have the range of 250 to 650 degrees Celsius. And obviously this is high, so this one is for a low temperature application, and mercury is for high temperature application. Besides mercury, there are things like sodium, and sodium would have the temperature of 600 to 1,200 degrees Celsius. Very good for high temperature application. So if you want to make sure that you could remove heat of some heated object at very high temperature, you would want a heat pipe with a working fluid that can accommodate that. So another one would be the material that's called indium, is even higher, to 2727 degrees Celsius. Right, so all these are for high temperature. On the lower temperature side, back again, sometimes they have a combination of various working fluids. So not necessarily only one type of working fluid. You can have a combination. So say, for example, ammonia. So ammonia would be working in the temperature range of minus 60 to 100 degrees Celsius. Kind of like, pretty good for a laptop, because your laptop get heated up, and that kind of temperature range looks like something, looks like a temperature that I need to change its phase from liquid state to gaseous state. There are also others, alcohol that I was talking about, and there are two types of alcohol. One is methanol, and the other one is ethanol. So the methanol in the region of 10 to 130 degrees Celsius, and ethanol 0 to 130 degrees Celsius. Now, comparatively for water, 30 to 200 degrees Celsius, depending on the silt pressure that you're dealing with in the heat pipe. In order for water to be effective, the kind of pressure that you have inside will need to be lower, because if the pressure is low,